I basically said this is the process that we go through. This is in zyBooks, and actually, what I'll add zyBooks section links to the module with the lectures that correspond to some examples. Basically, we get a circuit in the real world. So everything, we got a cosine source of some kind, and then we transform it to this phasor domain where everything appears in terms of impedances. All right, so in the time domain, it's a capacitor. It means I equals C dV dt. All right, but we transform it to this phasor domain where all of the voltages and currents are complex numbers. They're all phasors, right? So they're basically angles and magnitudes. Why do we do that? Why do we do magnitudes and angles, and why not keep the time function in there? I don't have to. I don't have to, basically. I mean, because nothing changes about the frequency piece of it, right? The only thing that can change in these circuits is the phase and the magnitude can change, right? So basically, this is our whole approach. This tells me basically this result here says I equals V over R plus 1 over J omega C. Basically, it says that the phasor for I, the magnitude and angle are whatever these are, and I can take the value of the magnitude and the angle and slap them back right into the time domain function. And I've gotten away with getting the steady state result without doing all of the grungy differential equation stuff, which is ugly if we do it that way. Okay. So what we started doing the other day was, I basically said all the methods of circuit analysis that you learned in 2111 apply also in 2112 with impedances. So the homework that you have right now, that's basically what you're doing. All right. So when I go through this here, the example I gave the other day is like Thevenin equivalence. So you got a couple of those I know on the homework. Thevenin equivalence, you say I got a network that's complicated. I don't even need to know how the stuff's connected in the network. It's just connected in some kind of goofy way, right? I got resistors, capacitors, sources, all that kind of stuff that's somehow connected. I don't know how, but somehow I can get it down to what is the open circuit voltage and what is the equivalent resistance. The equivalent resistance, this is the important point. It's the resistance that's seen by a load current. So in other words, if a current source was connected at those terminals, what would it flow through? That's different than saying what would a source inside that network flow its current through. All right. Those are totally different questions. So if I go with this, the way I think about this is essentially no matter how complicated that network was on the inside this box. So no matter how complicated the network was inside this box right here, all right, from the perspective of its terminals, when no load is connected, the voltage I get at the terminals is VOC. If I connect a load at the terminals, what I see is that the voltage at the terminals drops. It drops below whatever the open circuit voltage was. So what matters is what is the impedance that is seen by that current at the terminals. So we said this is useful, but basically this is what we're gonna do. So if we have no dependent sources, right, we figure out what's VOC, the voltage with no load, and then we figure out what is a load gonna do to that voltage at the terminal. So we need to know what the impedance is that current is gonna see. So it's the resistance seen by a load current. And the same is true for a Norton equivalent, right? The current you get with the highest possible load on the circuit, all right, which is if I put a short circuit across it, that's the current that will flow. And then the resistance that's seen by that load current. The resistance is the same. It doesn't matter whether it's a Thevenin or Norton. All right, so we're going to go through an example. And I left my notes downstairs where I have the number. That's going to be unfortunate. But I'm going to take this approach here and go through this. So I got two steps. I want to get a Thevenin equivalent for this guy. All right, and I should be careful. Really, I write this as VOC, but really this is in general, that's a terminal V. And the voltage that I measure with no load is called VOC, right? If I say that in general, there's some kind of a current flowing out here. Now, this guy here, this is in the time domain, right? I got to convert this thing over into the phasor domain. So what do I do to convert this thing into the phasor domain? That's the first step, right? What do I do? I convert what to polar? That cosine needs to go to that. So basically, I'm looking at this guy. He's got omega equals 10 to the 5th radians per second. So my phasor, I would say I have a phasor Vs, which would be what in this case? What's the phasor for 10 cosine 10 to the 5th t? Just 10. All right, so 10 angle 0 is what we would say. All right, so that's the whole thing I've got. So really, so I got to convert the circuit over into the phasor domain. And I'm going to write this as, I write V sub S with that bar. I usually write them as capitals. All right, and then I say I've got, I'm going to label everything just in, honestly, I don't find it particularly useful to use numbers. I know you guys like to use numbers. It freaks you out to use variables, but I can get a lot more intuition about what's going on when I use variables, right? Whereas when I look at numbers, it's just numbers. But I can check my reasoning if I keep them symbolically. So I'm going to do that. All right. So I'm going to call this, just to be consistent with what I did here. Okay. Z1. Okay. I'm going to call that Z1. I'm going to call this Z2. I'm going to call this here Z3. And I just put them as boxes because the impedances, it's kind of unclear whether they're capacitors or inductors or whatever. And so there's V right there, and then I would be right there. The step 1 in my process here is to get the open circuit voltage. Step 2 is to get the Thevenin equivalent resistance. I'm going to start with step 2, which is to get the Thevenin equivalent, and I should be careful, the Thevenin equivalent impedance. Okay. Now, just kind of level set here, what is Z1? What would I write for Z1? Yeah, Z1 is, I got a series combination of R1 plus whatever that inductor's impedance is, which would be what? What's the inductor? So L1 there is 0.08 millihenries. What's his impedance? Yeah, J times 10 to the 5th times 0.08 times 10 to the minus 3. Like that. Okay. And then Z2, what would Z2 be? R2 plus J omega L2. Yeah, plus its impedance, right? And then Z3, what would that be? I got a series combination now. R3 plus 1 over J omega C, which I can also think of as R3. How else can I write the 1 over J omega C? Minus J over omega C. One question that I ask you a couple of times, I think in the homework, is a particular impedance inductive or capacitive? Okay. And if I just told you, yeah, okay, if it's R3 plus 1 over J omega C, you know that, all right? But you know that there's a capacitor rather than an inductor. If I just told you that I had, I don't know, let's say I had 10 minus J10. Is that an inductor or capacitive combination? Capacitive, right? Because it's got a negative angle here. It's got a negative imaginary part. Is the real part ever going to be negative? It will not. I can't have a negative resistance. Not with resistors, not with a real resistor. Why? What would that mean? If I had a negative resistor, that resistor would somehow be generating power. Doesn't happen like that. All right. The laws of nature do not allow that. All right. So you'll never see that, but you will see a negative here, which implies that there is a phase shift, right? Because of this thing. All right, so I've got all that stuff. Now I don't want to keep them in terms of that because that's going to help me. I'm going to lose some intuition if I do this. If I do it like this, I can think of these like they're resistors and just do everything like Z1, Z2, and Z3 were resistors, right? And there's nothing that's changed about it. So I want to do step 2, which step 2 would basically be to say, all right, I want to find the equivalent impedance ZEQ looking into those terminals. And the way I think about this again is it's the resistance or the impedance that would be seen by a current source I at these terminals. So what impedance would that current source flow through? So it would flow into the circuit and then back out. And what we say is you know, if I'm worried only about what's the impedance that flows through this thing, I can basically turn off all the voltage sources and current sources, the independent ones, in the system when I do that. So first thing I want to do is I want to turn off the voltage source. So if I have a voltage source and I turn it off, what does that mean? Well, so let's think about it. So if I have a voltage source, turn it off, that does what? Makes its voltage equal to 0. All right. You're just thinking 2 steps ahead if you start saying it's a short. If I turn a voltage source off, it is a fixed voltage. Turning it off means that its voltage goes to 0. If its voltage goes to 0, it is now a what? A short. It's a wire, right? So a voltage source, right, can have any current flowing through it, right? The voltage source does not dictate the current flowing through it. The circuit does, whatever it's connected to. So when I turn it off, it basically becomes a 0-volt source. That's equal to a short. All right. So that's the way we think about it. So so what I do is I redraw this circuit and I say, all right, well, that means that if I turn it off, I've got R sub S all by himself. And then I've got Z1. I've got Z2. And I've got Z3. All right. Those 3 things are connected into my circuit. And here's what we have. All right. What we're talking about is what would the impedance is that would be seen from the perspective of this source at the terminal. So where a lot of you guys were messing up, and the people who were putting the things in the Discord last night, what they were doing is they were finding the impedance from the perspective of this voltage source looking that direction. You're going to get a totally different answer for that. All right, that's not what we're looking for. What we're looking for is the impedance looking into those terminals. So I start collapsing basically as far away from the terminals as I can. So I start my collapsing back here. All right. Now, so I want to go through this. I want to figure out what this guy's going to be. How do I do that? Where do I start? I want to start as far back as I can from the terminal. RS is in parallel with Z1. RS is in parallel with Z1. How do we know that? Their voltages are the same, right? That, in other words, if I do a KVL around this loop, right, their voltages are the same. Don't think of them as sharing nodes. Think of them as their voltages are the same. So I go through this step by step. All right. It's a bad idea to try to mentally do it all in your head at once. I do it step by step, and I try to collapse the network down from as far back as I can. So RS is in parallel with Z1. So I do it like this. I'd say, all right, well, now I have RS in parallel with Z1 as one combined impedance. And then I have Z2 and Z3 like this. And I'm back at the terminals again. I'm trying to find the impedance looking into there. In other words, I keep collapsing the network. The idea is everything about this circuit and this circuit is equivalent. They're equivalent circuits. In other words, the voltage here, right? The voltage across Z1 is the same as the voltage here. So if I called this, I don't know, Vx, right? And I called this Vx. The currents and voltages everywhere in this network are the same as they are everywhere in this network. They're equivalent circuits. That's the way of thinking of it. What's the next simplification I can do? Again, thinking backwards. You can do what? Well, so again, trying to go slow. There's a parallel and a series thing going on here, but the first thing I want to recognize is that I have what? The current is the same through Z2 as it is through RS in parallel with Z1, right? So these guys have the same current going through them, which means that they're in series. so what I would say is I have, I don't know, I'm going to say that there's some impedance Z4, which is Z2 plus RS in parallel with Z1. Yeah. How long do I think it should take? No, this is probably going to take us about, going really slow, probably going to take us about 15 minutes.
So like just like working on a
Should be, I don't know how long it should take you. It should take you as long as it should take you. Yeah. The question, I mean, the question really is how much do you, how comfortable do you feel with the logic? You get comfortable with this logic, you could do this in a minute. But it's all a question of where you are in that process, right? So you guys follow me there? Basically, those two are in series with each other, right? So now I say to myself, all right, I'm gonna collapse that down into. Notice one thing that I'm not doing too, which is helping me go faster, is that I'm not going to my calculator writing any numbers in. I'm not trying to get to numbers. I'm just trying to make sure that the symbolically this all sort of tracks for me. Then I can kind of put it all together. And I don't worry about getting numbers until I get to the very end. All right, so now I combined those two things. All right, now I still want to find the impedance looking into this guy. Well, what is that? The voltages across those two impedances are the same, right? So the voltages across them are the same. Then what do I know about them? They're in parallel, right? So now at that point, I can reduce this whole network to one impedance, which I'll write as ZEQ. And from the perspective of the terminals, that's the important thing. If I had, from the perspective of these terminals, the voltage and the current at these terminals is exactly the same as the voltage and the current at these terminals. So that's why the circuit's equivalent, right? That's why we use that term. So now I get to this idea that I got ZEQ, and ZEQ is equal to Z3 in parallel with Z4. All right. So I defined all these different impedances here. So if I want to keep this sane, what I said was ZEQ is Z3 in parallel with Z4. All right. And that is Z3 in parallel with, so Z4 I defined was Z2 plus RS in parallel with Z1. All right. Now, what I would do is I would go ahead and at this point, that's where I would now start making the equations however they need to be to put this in. All right. I'm going to jump ahead for a second to, here's the code that I wrote. All right, to put this into MATLAB. So what I did was I defined for myself my omega. I put in the values of all of the impedances here. And then I calculated, so here's calculating Z2, Z3, Z1, right? So Z1, Z and RS. All of my equations are in terms of RS, Z3, Z2, and Z1. All right. So what did I do? I basically then so I didn't call him Z4, I guess. What did I call him? That's why I should have kept my, instead of calling the Z4, I called this ZEQ2. And I called this ZEQ1. Okay. Do it that way. Doing what way? I mean, you label them however you want, I guess, but I think this kind of step-by-step process is the way I would think of it, right? So just to keep consistent, I'll say this is ZEQ2, and this here is ZEQ1. So what did I do? So what I did was I calculated ZEQ1, which is Z1 in parallel with RS, right? So I wrote that down nice and simple, and I can see the number and everything, and I can look at my equations. I can look at these equations, and I can match these equations to what I wrote by hand. I like that, right? That's why I'm not looking at numbers. I'm comparing equations. It makes it easier for me to track what I did wrong. ZEQ2 was, we defined it here. ZEQ2 was Z2 plus ZEQ1. And that is what my code has. All right. ZEQ was ZEQ2, right, in parallel with Z3. That's what I did here for ZEQ, right? So that allows me to keep track of things pretty nicely. And I ended up with some number for ZEQ, and I don't know what that is, but I get one. Okay. All right. So you guys follow that process? Important thing, and the main thing that most people get wrong is they start combining in the wrong direction, right? They don't start by the impedance looking into the terminals. They start back there, and they start saying, well, RS is in series with whatever's down here. You're immediately wrong right off the bat. Now you will need that though, if I want to say that the other step, which is to figure out the open circuit voltage. All right, so back to the original network here. So I had V sub S. I have RS. And then again, I just like drawing this stuff as simple boxes. I got Z1, and then I got Z2 and Z3. And then over here is where I'd find VOC. Okay. The voltage with no load connected. All right. So a couple of ways that I could do this. You could do nodal mesh, right? I'm not going to do nodal or mesh here, right? In general, I don't like to do nodal or mesh. I don't like getting two equations. Again, for me, intuitively, when I'm doing, especially when you get into electronics, it becomes simpler, I think, in a lot of ways to just kind of go through the process of simplifying the circuit, because intuitively I can look at my equations a lot better than I can if I just get a matrix of stuff. So how could I do this if I don't use nodal or mesh? No, I could do superposition, but it wouldn't help me. There's only one source, right? What's that? Z2 and Z3 are in series with each other. All right, he says, all right, let me take him slow. So that's all right. So he's saying, and there's multiple ways of doing this, none of which are wrong, as long as you don't make a mistake in the process. All right, here's RS, here's VS. So the observation that was made is that Z2 and Z3 are in series. So I have now this. Okay. VOC has disappeared from this. VOC doesn't appear. It appears here, doesn't appear here. Why? I mean, this is Z3 has been absorbed into that box right there, right? So ultimately, just think about where we're going with this. Who proposed this approach? Somebody out there did. Okay, so to get VOC, what information are you going to have to get ultimately? Yeah, well, so I would have, yeah, basically I would say it differently, but you're right. I'd have to get the current through here, I guess, right? Which if I had the voltage, I can get the current, right? So it's basically one difference. Same, 1/2 dozen. So as long as I can get this current, I don't know what I'm going to call that current. I'm running out of numbers. I'll call it IX. As long as I can get that IX, I can say that VOC is IX times Z3. You guys follow that? As long as I get the current in that branch, then I can figure out the VOC by using that current. All right, so how would I get the current in that branch? Couple of ways to do it. There's all kinds of ways to do it. I'll take whatever way you guys want to do it. Yeah.
All right, so convert the VS and the RS in current series, they can be a current source in parallel with the RS, and then do a current divider.
And then do a current. That's one way to do it. I could figure out the voltage across here, right? By doing a voltage divider. All right, but he wants to do a current divider. So you're doing my source transformation is what you're doing. You're saying VS and RS in series. Okay. So you're saying I get VS over RS is a current source. And then RS. The whole idea of any of these things, right, is that if I broke the circuit right here, then at those terminals, this and this in series are the same as this and this in parallel. In other words, at the terminals, this is always the idea, at the terminals, what's looking into this is exactly the same as what is looking into this. The V for any current I flowing out of these two, the terminals of these two circuits, the voltage is the same. That's what makes them equivalent. That's the whole idea. All right. So that's why we can do this. So we're always looking at things. I break them at terminals and I make sure whatever is behind those terminals is equivalent in the two different versions that I draw. All right. That's the way we think of it. So, all right, we do that, and then we have Z1 and we have Z2 plus Z3 over here. All right. So if I'm looking for, I called this IX. Okay. All right, I'm going to call this IS. So as to make this less ugly. Okay. All right. Mr. Current Divider. Since Ike, you proposed it, get us out of this jam.
It's a scary one.
All right, help me out. I know the current going into a parallel combination of things. So the first step we talked about the other day, right? So there's two steps to the current divider. What's the first step?
Figuring out the voltage. It's all parallel.
Figuring out the voltage, right? Figure out the voltage. They're all in parallel. So it's basically whatever the current flowing in is, which is IS, times the parallel combination of all that stuff. Yeah. Source transformation. If you're not sure, go back and watch the video. Right. So I did a source transformation there because those two things, VS and RS in series from their terminals, is exactly the same as VS over RS in parallel with RS. Right. And that's source transformation is a tool that you learned in 2111. So go back and watch that piece of it. If you're really not sure, we can take that offline and talk about it in some more detail. But I try to figure out the parallel voltage there. So basically what I'm saying is I've got, and the way I would do this is I would say, I always write RS as parallel stuff. I write the two bars like this. If I were to do this in MATLAB now, what I would probably say, the way I would really enter this is I would say it's IS. Again, I like looking at this because when I look at this, I can see that I got a current times an impedance, right? When I start putting them in numbers, I can't tell what the heck I'm looking at, right? I can't check units for myself. And I can't compare what I've written on paper to what I've written in the computer. All right, so for me, mentally, this is a useful process. Now, what I would probably say is that this is 1 over RS plus 1 over Z1 plus 1 over Z2 plus Z3 to the -1 power, right? That's the way I would combine those things. So technically, that was only the first step of what I'm supposed to write. So what that told me is what? That tells me the voltage across that combination, but I'm looking for the current IX there in my circuit. So how do I get the current IX? I guess really to be careful, I'm saying this is the voltage. I guess I'll call it Vx. Just to be really careful here. How do I turn that into Ix?
So I define the parallel combination V1 and V2 and V3.
No, because that would be Is.
Oh, it is just V2 plus V3.
Right, so I just want to know the current in that one branch. So I know the voltage across that branch. The voltage is, I know the current going into a parallel combination. That current splits three ways. And the combination of how it splits gives me the voltage, right? So I say it's whatever Vx is divided by Z1, I'm sorry, not Z1, Z2 plus Z3. And if I wanted to know the current in Z1, I would say it's Vx divided by Z1. If I want to know the current in RS, I would say it's Vx divided by RS. And if I added those currents together, what would they be? I sub S, right? So this is just telling me, I know that the current creates a certain voltage, and now I can just take that voltage, divide by the impedance in that branch to get the current in that branch. So I'm just using Ohm's law to approach it. All right. That got me Ix. And then I go back to my logic here, which said, okay, if I want to figure out VOC, I would then say VOC is that Ix times Z3. I could think of at least two other ways to do this, right? And I'm not necessarily suggesting that we use them all, but we could. All right. You guys want me to do another approach to it?
Yes, we sure. I need all of them. I think it's like-
You know, all the ones you can get. I will, and let's do that on Friday. We got a lot of time together on Friday. Too much time. You guys get tired of me on Friday. So, and I posted, you know, this example fully worked out for Monday's lecture. All right, and it includes the code here. All right, that I used. Okay. All right. And I think if you look at what I did, I think my approach for doing this is effectively the one that we just took. All right. What I did want to talk about though is I wanted to start going through, because we're just gonna keep talking about methods. So I'll do more examples of the combining of stuff on Friday. Talk about the node voltage method, right? Because some of you guys are still confused on that. I saw that clearly in the first exam. All right, so when I look at this guy right here, the way I think about the node voltage method, we set one of our nodes to be ground. So in this case, how many nodes does this circuit have? Technically it has 4. Yeah. All right, so I got one here. I got one here. I got one here. I got one here. All right, now how many unknown nodes do I have? 2. All right, so you always set one to be 0. You set one to be ground. Okay, and we use that term ground. All right, we don't talk about that much, but ground is that middle, it's the little pin on the outlet. And it is, I'm just kind of arbitrarily making it here, but any real circuit you build, you actually have a connection to the earth, like to the dirt, right? And you make that connection via a pipe or something into the dirt. All right, so any real circuit that you build, you have a connection to ground. That's why we call it there. And ground is defined to be 0 volts. All right, so we use that symbol for it typically. All right, what I do here is I define for myself all the branch currents, the currents in each individual branch there. All right, so I defined I2, I4, I3, and I5. Why I didn't start with I1, I don't know, but I've got I2, I3, I4, and I5. All right, now in the node voltage method, the way we think about this is each circuit has n independent nodes, and we designate one of those nodes as the ground. And again, we use the term ground because most circuits, there truly is a connection to earth ground. What you're doing, if I have n independent nodes, I always have n equations. and there's one for each, the voltage at each node, right? Each node voltage is a voltage with respect to ground. It has absolutely nothing to do with Ohm's law. All right. In other words, if I say, in this case, we're going to end up calling this guy here, I'm going to call this V1 and I'm going to call this V2. That has nothing to do with the voltage across any individual resistors. That is the voltage. So V1 is how far above zero this node is. And V2 is how far above zero this node is. All right. Now we're going to use those to write Ohm's law, but Ohm's law doesn't have anything to do with them. Okay. All right, so what I do is I write a set of KCL equations that solve for the node voltages. All right, so Kirchhoff's current law is giving me voltages. In the mesh method, Kirchhoff's voltage law is giving me currents. All right, so it's a little bit confusing in that regard, but I write KCL equations and write them in terms of the voltages to solve for the voltage. All right, important thing to remember. Voltage is always measured across something. It's meaningless to say what's the voltage at a point. If I say what's the voltage at one terminal in a circuit, that is a meaningless statement. Voltage is always between 2 points. All right, so if I'm talking about a node voltage, it's the voltage between here and ground. Voltage between here and ground. All right. When I talk about why that matters is the thing everybody screws up is they don't remember that part. And there's actually multiple steps to writing the KCL equations correctly. I actually have to write the Ohm's law equation correctly for each of these things. So the way I think about this is, all right, I defined here I2, I3, I4, and I5. All right, so what I do is I also define voltages, right? So based on the way that I defined these, I say, okay, well, VA is the voltage across that combination of R2 and R3. So VA I would write as I2 times R2 plus R3, like that. And so then I would rearrange this and say I2 is equal to VA divided by R2 plus R3. Now, VA can be then written in terms of the node voltages, right? So I look at the plus and I look at the minus and I say, what's the node voltage at the plus and what's the node voltage at the minus? What is the node voltage at the plus terminal of VA? It's whatever that V0 is. And then the node voltage at the negative is V1. So I write it like that. This can now go into my KCL equations. All right, so the way that I look at this is I basically always define everything that way. So then if I say, all right, how about for I3 there? I3 is V, so I labeled the voltage across this resistor as VB. So it's VB over R1, like that. So that's not in terms of node voltages. So in other words, all of these, so I define my currents. You guys think I'm slow and you don't like to do it this way, but I don't make mistakes, right? Because what am I doing? I define the currents. I can write my KCLs in terms of the currents. I write the voltage across these things and I can track the passive sign convention and all that stuff. Thing to remember is there's basically 3 steps. You're writing KCLs. You're writing Ohm's laws for the resistors. And then you're also then taking the voltage across the resistors and defining them in terms of the node voltages. There are 3 distinct things that are happening. And so there are 3 times that you can screw up the signs. All right. I guess if you screw up the signs twice, you're okay. But if you screw them up an odd number of times, you're not. All right. Which is where you guys make the mistakes. Okay. All right, so do it slowly. So define the currents in the branches, then define the currents in terms of the Ohm's law relationships, and then define the Ohm's law relationships in terms of the node voltages. All right, so I3 I said is whatever the voltage across R1 is, that's a VB divided by R1. Now, how does VB get defined in terms of the node voltages? V1 minus 0 specifically. It's the voltage of the plus minus the node voltage of the minus, right? So it's V1 minus 0. All right. Then if I kept doing it here, so I would say then for I4 would be, how would I write that using this approach I've been trying? Using this approach I'm using, I would say it's VC divided by R4. Now, again, you guys think I'm being slow and old about that, but it's going to help me keep track of stuff. Because because I might run into a passive sign convention problem later, right? Because I remember my Ohm's laws need to be written a certain way with the passive sign convention. So now I look at this and I say, what's the node voltage at the plus terminal of VC? It's V1, right? Minus whatever node voltage is at the negative terminal, which is V2. So it's that. All right, so that's how I go through that process. And then I basically say to myself, all right, I have two nodes, so I have two KCLs to write. So how do I do that? The way that I do this, I look at my KCL. So let's do node 1 first. What would that be at node 1? I2 is the current in. That's equal to I3 plus I4, the current's out. So I do it that way. I say currents in equal currents out. Now, I think the way Zybooks does it, I'm going to try to square that up here in a minute. Zybooks does it as all the currents into the node. It just thinks of all the currents into the node and then sets that sum equal to 0. I don't like that approach, but the results that I get and the results that it gets are the same because we take care of our signs. All right. What about for node 2 here? What would I get for that one? I have I4 is into the node. I also have another current into that node, don't I? Yep. I5 is the current going out. I0 and I4 go in. Now, why this is important, like on that first exam, you guys gave all kinds of answers. But I look at this, this is a KCL, amps equals amps plus amps. Amps plus amps equals amps. All of those are in terms of amps. If I'm careful about that, how do I know they're in terms of amps? Because they're volts over ohm. But I can track to make sure. When I get super nodes and stuff, I see you guys doing all kinds of stuff where it's like volts minus volts equals amps, right? And so you see all kinds of crazy stuff forming. One thing I like to check is when I look at these things, I can see what the units are. All right. So in terms of what I ultimately end up with, right, for my nodes, I guess I wrote them here, right? So you would then plug in these relationships on the left side into those equations. And let's just do node 1 for a second here in the limited time we have. So I said I2 equals I3 plus I4. And based on the way I wrote that stuff on the previous slide, I have V0 minus V1 over R2 plus R3 equals V1 over R1 plus V1 minus V2 over R4. All right. That's the result that I get. And you can do node 2 similarly. But I want to do a check. If you look at the Zybooks method, all right, so I took this guy from Zybooks. What they do is they basically end up saying, just think of the currents going on. I don't like this. Mentally, this is not something that I like to do. Did you guys learn it this way in 2111? All right. Does anybody do it this way? Don't be ashamed if you do. Who's he? Yeah. Who's he? Yahoo or Hassan? Yeah. So does anybody do it this way?
Because I gave invited.
Think about this. We'll talk about it more on Friday, right? I don't ever do it this way. What I do is forget about the directions. I make my own directions and then I'm consistent with the rules, right? As long as whatever you write is consistent with whatever definitions you made, then it's fine. When I say consistent, what do I mean? I mean that I follow the passive sign convention. And that's basically it, right? I followed the rules of KVL and KCL. right? I personally, this drives my mind nuts to have two currents in one branch going like that. Now you can, but you end up reversing Ohm's law in the two. So it hurts my brain a little bit. I can talk about this, but if you guys don't think of it like this, I would recommend that you think of it like this. All right. All right. Now on Friday, we've got recitation and we've got class. So we're going to do tons of examples between those two for sure. Okay.